Hello, my dear students. Welcome back to the lecture. So, in this lecture, we'll try to solve the slab BBS for this particular building. Okay. So, before that, you may have few questions in your mind. Like, sir, from where did you take this L by 4? From where did you, sometime, like I told you, top extra bar in one of the drawing, they give you this L by 3, isn't it? See here. Here it is given L by 3. So, from where all these things comes, right? From where you are taking the values L by 4 and all. So, usually, these values are taken from the code book. You have to go to the, I'm just showing you. If you want, you can download this from the Google. So there's a code book, my name, SP34. Okay. It's written SP is for special purpose 34. And if you go to the page number 127, so they have shown it here. If you're using a straight bar, something like this is what you're supposed to follow. Right now, I'm teaching you for the crank portion, isn't it? So this crank portion will come like this. It will come like this. It got a crank, right? And it will go like this in this way. Got it? So this length you can see now, it is mentioned from the center of the beam to from the center of the beam to this portion, it is 0.15 into L1. Okay. Similarly, the next bar what you have is that you are bringing your bar from here. You're bringing your bar from here and it will get a crank. It will be over this only. Okay. And it will go straight like this. It will come like this actually, but it is behind this particular bar. So it's not visible. I will not show that. Okay. And this length, crank length, what you have, this crank length what you have from the center of the beam to this is 0.25. What is 0.25 into L1? It is L by 4. L by 4 means 1 divided by 4. 1 divided by 4 is 0.25. So 0.25 into L1. Simple. Again, that is how all these things comes into play. That is why in the drawings and all, directly they mention it has to be L by 4. Got it? That option is clear. Now, in most of our calculation, I took L from the clear span. That is, if this was my beam, this was my beam. From beam inner to the beam inner, I took it as L. But few people, what they do, if you refer the code book, these people also have taken L, but these people have given L from the center of the beam to the center of the beam. We used to take from the clear span, that is from the inner, from the inner of the beam to the inner of the beam, I used to take. But in the code book, it is written from the center of the beam to the center of the beam. And this is your L1. So based on the drawing that is given to you, based on that, you are supposed to take. Getting my point? Okay. But for my calculation, I took everywhere clear span L, and that is also a right way of doing. But few people follow this code book from here, and based on that, they do. And in that case, your 0.25, that is L by 4, will be also from the center of that. We took from the clear span, right? That is from the beam inner, from the beam inner face, I took L by 4. But if you're following something like this, then your L by 4 is also from the center of the beam to this. So there won't be much difference in the answer. Hardly like, a 10, 15 difference is gonna come, but that's fine. You're getting my point. Now, along with that, we saw here in this drawing, they are given this L by 3. That was your top extra bar. This was your top extra bar. This was your top extra bar. So what was that? It was given L by 3 from the center of the beam. So again, where it is written. So in the code book, if you come, you see here, this is your top extra. This is your top extra from here to here. You can see this one. This is your top extra. So what is given? Top extra from the face he has given. From the face, it has to be 0.3 into L1. What is 0.3? 0.3 is actually L by 3. Actually L by 3. But if you do L by 3, you get 0.33. But in the code, they are taken to be 0.3. Again, L1 is from this center to this center. Getting my point? The usual practice is that your crank will be L by 4 and your top extra will be L by 3. That is a reason practically, whenever the crank was given, yeah, I think this image will serve the purpose. Yeah. That is the reason practically. Can I see any top extra here? No, this is not visible. No, I think there is no top extra. There is no top extra. Wait, there is a top extra. Let me play this video. Yeah, you see here. So this is one bar which has come, which has got a crank and gone like this. Next bar, it has come like this, got a crank and it has gone like this. In between the two crank, you are going to give a top extra. So this is my top extra. Can you see the length of the top extra? It has stopped something. So this is L by 3. So that is why your top extra will be almost like 150, let us 75 to 100 extra than your crank. If your crank is ending here, your top extra, if your crank is ending here, top extra will end here. So this and around 75 to 100 mm further we are taking, because it was L by 3, because L by 4 is 0.25, L by 3 is 0.3. The obvious, a small extra length has to come. That is why practically, if you see, you can see here also practically, see, this is little more. Your crank is ending here, but this length has come forward. Similarly, your crank is ending here, but this length has come forward, right? So that is how it is practically done. But few people do L by 4, L by 3, few people do L by 4. It's okay. It's totally up to you, up to the structural designer, how he's trying to do that. Okay. Yeah, I think you can see all those things here. Hmm? Yeah, here also you can see that, no? See, this was your top extra. It has come like this. Huh? Sorry, it is here. This one, top extra. See, it will come like this. Top extra, come like this. In between the two crank, you are providing top extra. Between two crank, you are providing a top extra. Okay, clear, no? Fine. Now, coming to the main question. Fine. Everything you understood. But why that has to be done? And why this is 0.15 into L? So see, one thing you have to understand. This thing, whatever you can see, crank I understood, sir. You told it is a L by 4. So from the center, I'll take 0.25. If crank is L by 4, then why this crank they have taken 0.15? Then why this crank is taken 0.15? Because this is also crank bar. From the top, it will come, it will get a crank. So he is telling you take this as 0.15. Just now you are telling you have to take 0.25. But again, you are telling here it is 0.15. Why is that so? So to understand this, I'll tell you one thing. I'll go with a drawing. Okay. So from the drawing only, you have to understand it. Yeah. So this is that slab panel what we have. Okay. This is slab panel 1. This is your panel number 2. This is your panel number 3. This is your panel number 4. So draw the bending moment diagram of this. So if you draw a bending moment diagram of this, the normal bending moment diagram is, it will be 0 here, maximum bending moment, and 0. I'm taking one, I'm considering it to be simply supported. So 0 maximum, 0 max, sorry, 0 maximum. This is 0. Here maximum sagging bending moment will be, here the moment will be 0. So this is a typical bending moment of the slab. But now, since beam and slab is casted monolithically, I'm using a term called as monolithically. So this is your beam, this is your beam, this is your slab reinforcement. The slab reinforcement will come and sit on your beam, and it will get a small development length. And whenever a load comes on your slab, it will try to make this beam also bend. So there is a kind of a fixity because you are adding a concrete. Steel also will have that bond. So because of the bond between the concrete and the steel, a small fixity will arise, and this fixity will tell the beam you also try to rotate with me. So since this small rotation is happening, it is creating a kind of a fixity. So that is why, because of this, what is happening, a negative bending moment arises. Because of this, a negative bending moment arises. That is why the typical bending moment diagram of a slab and a beam will be something negative. You get a positive bending moment, and you get a huge negative, you get a sagging, you get a huge negative, you get a sagging, you get a huge negative, you get a sagging, and a small negative. Got it? Understood? Now, why did this bending moment change in this way? Due to the bond between the, exactly, beam and the slab, due to the monolithic casting. So if you ask me what is monolithic casting, this is monolithic casting, right? See, everything is continuous here. If I show you this complete panel of a slab, see, everything is continuous. You see, you have a beam, you have a beam, you have a beam, you have a slab, and because of that, what will happen? So you get a bending moment like this. Okay, got it? We didn't want that bending moment to happen. I didn't want that. I wanted a simply supported only. But due to the interaction between the beam and the column, and due to the reinforcement, indirectly that is happening. That is why the code says. So that is why the code also says. I think it should be here. Yeah, see here. Good. At a discontinuous edge, negative moments may arise. They depend on the degree of fixity at the edge of the slab. But in general, tension reinforcement equal to 50% of that provided at the mid-span, extending of 0.1 L into the span will be sufficient. So because of that, there arise a negative bending moment. In order to take care of that, we are going to uh, that is why the negative bending moment happens. So that is why what we do, we try to give that top extra bar and all to take care of this. This much is understood? Fine. So I'll go back to this and quickly I'll explain why it is 0.15. Now I'll draw one line here. Let me draw one line here. So this is that center portion line. Now tell me, the bending moment what you have here is little high. Okay. In this portion, this much portion, this bending moment, I'll shade it now. This portion, this is negative bending moment, no? This is little higher. This is also negative bending moment. This is also negative. Whatever is above the green axis, it is negative. Whatever is below the green axis, that is your positive. That is your sagging bending moment. So if you want, I'll write that sagging also. This is sagging. I'll write plus. I'll write plus. This is sagging bending moment where you provide a bottom strain. Now, let us say the bending moment what I'm getting at this junction is, let us say I'm considering 145 kilonewton. Just a random value I'm considering. Okay, 145 kilonewton meter. Here also I'll write 150 kilonewton per meter. Here also I'll write 148 kilonewton per meter. Whereas near the support, here the bending moment is very less. Of course, it is a negative bending moment, but it is very less compared to this. I'll consider 50 kilonewton meter. 50 kilonewton meter. Here also I'll consider 50 kilonewton. Let us consider. Good. Now tell me, wherever this continuous support, this is continuous because you have a beam here, you have a slab in this panel, you have a slab here. You have a beam, you have slab in this area, you have slab in this area. You have a beam, you have a slab in this area, you have a slab in this area. Whereas this is called as edge beam. This is your edge beam and this is your edge beam. That is why in the SP34 he is mentioning edge beam, right? So he is mentioning if it is an intermediate beam, that is a continuous beam. This is edge beam. So practically this is my edge beam. This is my edge beam. Edge beam. I have a slab in this panel. I agree. Do I have a slab in this panel? There is no panel. I mean, there's no slab on this particular beam. I have a slab on this side. Good. But do I have any other slab? Do I have any other slab in this direction? No, it's a discontinuous. So because of that, what will happen due to unbalanced moment here? What will happen? Your bending moment is very less. Now, since your bending moment is very less, you don't have to provide your crank bar when you provide a bar, right? You have to provide your bar, no crank bar, because negative bending moment will come. So your bar will come. I'll do it like this now. Now you'll get the complete idea why you're doing that. So your bar will come, and if you give a crank like this, it is enough. And you take a bar straight. Now here a more crank is required. Here a more crank is required. Why? I'll tell you. Here it will go straight. Here again more crank is required. L/4 crank is required. Sagging crank is required. Okay, I'm doing this type of crank. I hope you are able to understand. Okay, here and here small crank is enough. Okay, so usually the crank length, what we follow, what SP34 says is that wherever there is a continuous support, you have to give L/4. So I'll give L/4 now everywhere. Okay, this will be from the face of my, okay, I'll take from center to center. This will be L/4. This also is L/4. This is also L/4. This is also L/4. This is also L/4. This is also L/4. But whereas at the edge beam, this is edge beam. This is also edge beam. What my SP34 says, at the edge beam, you give only 0.15. You give only 0.15. L/4 was here, no? See here. 0.25 into L1, 0.25 into A. That is L/4 I did. Getting my point. Now, here what I'll do, I'll say no. Only 0. How much it was? 0.15. 0.15 is 1 by 7. Okay, I'll write 0.15 into L. Into L, I'll write this crank length is 0.15 and this crank length is 0.15 into L. That is enough. Got it? But you understand why? You see the intensity of your negative bending moment is only up to here, no? When your negative bending moment is only up to here, you don't have to provide your crank like this. Up to here, your crank is not required. Why? Because your intensity is only up to here. Only up to this negative is there. Top speed is required only up to here. So that is why what we do. We reduce that crank length. We say only up to here crank is enough. From here, you take it bend and go like this. But whereas here, your negative is starting from here. So we'll stop here and from here, we'll give a crank. We'll take up to here. Your negative is up to here. So I'll take up to here. Then again, you'll give a crank. This is my positive bending moment. Again, your negative will start from here. I'll give a crank, take up to here. Negative is up to here. So I'll give a crank. I'll take it here. Again, your negative is starting from here. Give a crank. I'll take up to here. Okay. Getting my point? Negative. So negative is fine. Now again here you see, in this portion you see your negative is very small. So up to here I go, give a crank and take it up to here. Got it? So since your intensity of negative bending moment is very small, they say, the code says only 0.15 into L if you provide crank length, that is enough. Where at the discontinuous support or at the edge beam. Whereas center portion, both the side you have slab. So because of that, what will happen? Because of that, you have this long L/4, L/4. So L/4 from here, L/4 you're supposed to give. Got it? Understood the concept? Now, that is the reason whenever you refer the code book and all, they say 0.15, 0.25. But again, everything is only on the paper. That means everything, whatever I explained you so far, that is a concept which no one will tell you. But that is only on the paper. But practically, we don't do that. Practically, even though your negative bending moment is very small, we don't again give 0.15 into L1. We take L by 4 only, because it is easy for me to teach you. It is easy for you to understand. But practically, do you think it is possible to do on the side? It will take long time. So even the bar benders will get frustrated, because edge beam he has to find. Then he'll do 0.15 into L. Continuous he'll do again this. Instead of that, take L by 4. No problem. If you do L by 4, what will happen? You're on the safer side only, because minimum is 0.15. Are you going even lesser than 0.15? No. You're going more than 0.15. I mean 0.15 is L by 7. You're not going lesser than L by 7. You're not going L by 8, L by 9. You're going L by 4, which you are more safer. So that is fine. In civil engineering, you have to be safe, but you should not come down that range. Whatever is given by the code, that is a guideline. See, this much minimum I want, right? So you feed more than that, but too much is also not good. But at least instead of L by 7 or 0.15, I'll go with L by 4. That is the reason practically whenever you go to the site and all, we try to keep L by 4. But this is what, but there are few consultant who says no. I'll show you one. I mean, I don't have a picture, but there are few consultant who say that no, H beam you keep 0.15, and few people do that whenever you have a large slab panel and you feel by doing this you are making a structure economical. In that case you do. But if you have a small, let us say if it is a small building like this, I mean, it's hardly you have any slabs here. 1, 2, 3, 4, 5, 6. So how many edge panels you get? One edge slab, two, 3, 4, hardly 7 to 8 panels you get. You don't save a lot of steel in this. In that case, you give L by 4 everywhere. Here also he has given, see, here also, even though it's a edge beam here, he has given L by 4, L by 4, L by 4, L by 4. But if it is a large span and all, and if you feel by doing L by 7 or 0.15, you're saving a steel, you can do that. Few consultants do that. Got it? So you understood the complete history of all these things, because doing a BBS anyone can do. You should know why these concepts are being done. Tomorrow, if something goes wrong on your side, so you should know. You can educate somebody else. So this is a concept. It's okay if you do it something like this. Okay, that is why you see even here in the picture he has shown that the small crank he has given, but here the crank is little bigger. Okay, yeah. And for the same project, I have a video. I mean, there was a video. Yeah. Anyhow, it's not required now. Okay, understood it. The entire concept you understood. Fine. Now we'll go with the BBS part of this. So take this one single panel and try to do the BBS of this. Very simple. So yeah, for that what I've done is I'll go to the Excel. Yeah. So this is that picture what I have. I think where is that? Yeah. The same thing I've taken here, and this is the size what I've put. Okay, you have to follow this size so that my calculation is easy. So all the beams are 230 by 450. The width of all the beam, what you can see here, B25, they are 230. And this panel is I've taken 5 meter by 7 meter. So that for previous Excel sheet, I've taken the same dimension. Here also I'll take the same dimension so that my calculation is simple. But if you want to practice, you take a different dimension and do it. But I'll take 5 meters, so my calculation is easy. So this is 5 meter, this is 7 meter, this is also 5 meter, this is also 7 meter, this is 5, 7, 5, 7. Okay, simple. Now first bar we are going to place in the shorter span. So you'll put a crank, you'll take a top bar, you'll give a crank, your bar will go like this up to here. Then next alternate crank, you'll start here, give a crank like this, and you bring it here. So in this way, these are your main reinforcement which you put in the shorter span, alternate crank. Once you finish this, next you are going to put the, not the distribution bar, because it's a two-way slab. So again, this will be a main reinforcement. Give a crank, take it like this, and alternate bar. That is, you start from here, give a crank, and bring it here. Got it? This is how you're supposed. It's a two-way slab. Now you'll ask me one question, sir. How did you say it's a two-way slab? Very simple. When they give a dimension, when they give a simple symbol, something like this, you see, this is two-way slab. If the symbol is only in one direction, it's a one-way slab. This is also 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 one-way slab. But this is two-way slab. Look at the symbol here. It is something like this. That means it indicates that your load is going on all the four beams. 1, 2, 3, 4. Again, this is, again, practically all are two-way slabs only. There's nothing like one-way slab. Okay, that also I explained you. Why? Because practically I know that load won't go. Do you think on the real structure the load will not go on the other two beams? That will go. But the intensity of the load which goes on the other two beam is very less. So if you do that derivation, it has been seen that If it is a one-way slab, for example, see, I'm telling you a lot of things from theory point of view, which is actually required, because doing BBS anyone can do. Okay, but if you don't understand the concept, it will be difficult for you to sustain in the industry. If somebody asks you a question, you should have a logic to that. You should have a proper understanding of a subject. Yeah. So if this is a one-way slab, because the load is going in this way, so it indicates that your load is going on this beam, your load is going on this beam and on this beam. Okay, I mean according to the theory. But do you think practically when a load comes on this, that beam says no, no, load will go only on this beam and this beam, and these two beams will not take any load? Do you think that these two beams will not take any load coming on this slab? They'll take the load, but the intensity of the load going on this two beam is very less. How much less? It has been seen through a derivation that 95% of the load, if 100 kg of a load is coming, 95 kg of the load will go on this and this. That means 95 means almost 47.5. Okay, half of load will transfer, because you know how the this load distribution will happen according to the yield line theory. The load distribution will happen like this. You will get a cracking pattern like this. It will crack like this. So it will crack like this. It will crack like this. It will crack. So it is a trapezoidal and a what is that? Trapezoidal and your triangular distribution. So this much amount of load will come on this beam. This much amount of load will come on this beam. Whereas on this and this, very little. How much? 5% of the load will go on this beam and this beam, where we say it to be a negligible amount. That is why we consider this to be a one-way slab. But practical load goes, but very small amount of load goes. That is why we provide minimum reinforcement in the opposite direction, which will take care of that. Understood the entire concept? Okay, this much is enough. Now we'll start with the BBS part. So first we'll start with this shorter span bar, 5-meter bar, and then we'll come with the longer span bar. Now we'll be taking one panel at each time. Now don't tell like, sir, this panel, this, yeah, of course. When you do practically, you'll not be cutting a bar something like this. You don't cut a bar like this. You'll stop. You won't stop. You'll take a bar continuous. Then your next bar will start from here. It will get a crank. It will come like this. Practically, when you do the construction, when you do the execution, you'll be putting a straight bar. But if you have to do in that way, your BBS will be so much difficult. So what we do is we go with panel by panel, and whatever answer we find, it will be almost 90 to 95% accuracy will be there in the answer. 5% variation may happen in your steel. Okay. But we'll do according to the panel wise. This much is understood? Fine. So I'll take one panel at a time now. So this is a panel what I'm considering to do the BBS. Oof. Yeah. Okay. Now quickly start with the calculation. Already done and kept it. You have to do your own Excel sheets. And you know how to prepare a shape, something like this. Everything I've explained. Now tell me. Okay. So it's a 5-meter. So again, crank length and all is L by 4 here. So take it. So this is 230. 230 minus 1 cover I have done. Plus this is 5000. Okay. Plus this is crank. This crank length I want to add. It is L by 4. 5000 by 4 is again 1250. So minus 1250 I did. So I got 3955. So this is 42. This is 0.42 into H. And the thickness of the slab is 150. It's not told by me. It's given in the cross section. I think, see here, they have written 150 thick. Okay. The thickness is 150. So everywhere it is 150. But in case if you want to change it, if you want to do some trial, you take it as 200 and do the calculation. You'll get a different answer. If first you do according to 150, later for the practice, you change the dimension to 200. Okay. Good. Yeah. Where was I? 42 you got. And this is 1455. Why? Because this crank length, I know it is how much? 1250 plus 230 is a beam width minus 1 cover I'll do. So I'll get 1455. So I've written this is main bar along the shorter span. So what is the dimension given? See here. It's a 10 diameter bar. Okay. They have mentioned 10 hash at 150 center to center. So 10 diameter. Spacing is how much? 150. No. So make it as 150 now. Okay. Wait. Not this one. I should start with this. Sorry for that. This is that project. Hmm? Yeah. Okay. Okay. I'll put it here. Hmm. Okay. What is the spacing? See, spacing has given 150. But this time what okay, I'll put 150 only. Will not confuse you. 150 spacing. So how many number of bar we got? 48 number of bar. How is that? You have to take the opposite length. Opposite length is 7000. 7000 divided by 150 plus 1 you do. You'll get 48 number of bar. So total cutting length will be how much? You add everything. Like 3955 plus 42 plus 1455 minus 2 into D. So 2 into 10 if you do, you get 5432. In terms of meter, it is 5.432. So total cutting length is again this one multiplied by number of bars into 1, and it will be 260.736 is the total cutting length. Weight will be 260.736 into 0.617, which is 160.87 kg. Okay, got it. Now the question is that practically, like I told, all the bar will not be put like this. You are going to put a alternate bar, isn't it? First bar will start here, you give a crank, you bring it here. Next bar, you start like this, you give a crank, you bring it like this, right? So in this Excel sheet, I'll create that bar also. So I created that bar. You have to create the same bar. See, Control C, Control V. Whatever shape you have created, Control C, Control V, and then you rotate it like this, in this way. And once you rotate, you reverse it like this. Finish. Your bar is shape is ready, and I have kept it here. Is it like this? Yeah, this only. I think it should be like this. No? Yeah, it is like this. Done. Alternate crank you got, no? One crank straight, crank and take it here, next straight and crank and take it here. Got it, no? Yeah. So again, same thing. Whatever you got 1455, that I've written it here. This crank length is 42, I've written 42. The straight was 3955 here, the straight is 3955 here. Again, I've written main bar along shorter span. So I written this as crank 2. Because since it's alternate crank, this is crank 1, this is crank 2. Got it? Fine. Now, spacing you see here. Spacing you should do 300. If you're doing in this way, the spacing should be 300. Why? Because if I'm putting this bar first, next bar will be this one, right? After that, again this bar will come. So the difference between these two similar bar will be 300. Spacing is 150, but difference between them is 300. That is why 300 I did here. So 25 number of such bars you are going to place practically, and here also I did 300. So you're going to put 24 number of such bars here. Getting my point? So if I add both, 25 plus 24 is 49 number of total bar. Even if I do 150 here, I'll get the same thing. 48 I get. So 1 bar variation will happen since we are rounding up and all. That is the reason. But it will be right answer what we are doing. So you're getting my point, right? But one thing you remember, when you're finding the bar for this one, again you should not do +1 here. Why? Already +1 you have done for this. Already +1 you are done for this, so you don't do +1 for this. If you do +1 for this also, 2 times you are adding up. So practically when we do in a single stretch, we add +1 only once. No, that is why either you add +1 here or you add +1 here, no problem. Okay, fine. So previously you got 48 number. If you don't do like, if you don't bifurcate that, we had got 48 here. Same thing we are getting here. 25 plus 24 is 49 number of bar. So 1 bar extra will come here, but practically on the side that extra won't come. It will be 48 only, because since we are rounding up and all, say I've done a round up here. Here also there is a round up and all. And this 7,000, we don't exactly place at 7,000. It will give a small gap and we place. So practically 48 number of bar only will come. But again, with the calculation here in the Excel sheet, sometime you will get one extra bar, and that is fine. You can go with that. Okay, fine. So again, cutting length, you know how to do. You add everything, 1455 plus 42 plus 3955 minus the 2 into 1 into D you do, you will get it. So total weight will be 5.42 into 24 into 1. This will be 130.368. It's a 10 diameter bar. So 130.368 multiplied by 0.617, it will be 80.4371 kg. So you got the crank bar along the shorter span. So if I add both the weight, that is 83 plus 80, I'm getting 164 kg. And if I go back here, only in a single stretch if I do, I'm getting 160.874 kg. So almost 3 to 4 kg difference will come sometime. But on the side that can be, taken care of. Okay. Yeah, if you're doing it separately, this crank separately, and add it, you get 164 kg. But if you don't separate it out, in a single stretch, if you try to do that, you get 160.874. Okay. Got it, no? So shorter span I've explained. In the same way, now we are going to do along the longer span. So again, same thing, longer span. This time your length will be 7 meter. Okay. So I've written here main bar along longer span. So I've given this is 5455. How did you get this 5455? This is 230. Where it is? This is 230 minus 1 cover. So 230 minus 1 cover. The straight length is 7,000. So 7,000. Okay. Minus this is 230 and 1 cover. So that is why you are getting this one. Okay, sorry. The straight portion we are supposed to find, no? Okay. I'm supposed to find the straight length now. Okay, good. So the straight length will be 230 minus 1 cover plus 7,000 minus this crank length. So it is 7,000 by 4 will be 1750. So if I deduct 1750 from here, the straight length I'm gonna get. Now again, that coming to this crank portion, so it is 0.42 into 90 because it's a longer direction. Already a shorter span 10 diameter bar is coming. Over that your crank is coming. So 150 minus top cover minus bottom cover and minus your shorter span dia minus this dia if you do, it will be 90 mm. Okay, that already in manual calculation I've explained you. Again, this will be 1955 because your crank is 1750 plus 230 minus 1 cover you are supposed to do. Got it, no? And now main bar along longer span, you write this crank 1. This is crank 1. Okay, because another crank also I'm going to do. One number of member is 1. Dia of the bar is 10. It is mentioned. See, nothing I'm assuming. I'm taking everything. It's written here. If you don't understand, see here. See in the drawing. Your longest span bar, it is written 10 diameter at 150 center to center spacing. Shorter also 10 dia at 150 center to center spacing. Okay. Same thing I'm adding it here. So 10 dia. But spacing, what you do, since I'm finding alternate crank, I'll double the spacing. So it will be 300 here. Okay. If you don't want to do 2 times, then you write 150 here. Then your answer will be 35 here. But since I'm doing it individually, this crank I'll take out separately. This crank I'll take out separately. In that case, what I'll do, I'll increase the spacing 300. So 18 number of bar will come. Again, 5,000 divided by 300 plus 1 if you do, you'll get 18 number of bar. Cutting length, you add everything. This minus 2 into D, bend deduction. It will be 7427.8, 7.4278. So total cutting length will be this, multiplied by number of bar into this one. It will be a 133.70. Since it's a 10 diameter bar, so I'll add it. 133.70 into 0.617, it will be 82.4931 kg of a steel. Now same thing you do on the other side. Whatever shape you have done like this shape will be like this now. Straight bar, crank and this. Whatever you written here, 5455, that I'm writing it here. 37.8 crank length, same thing. This portion is 1955, 1955 I've written. Got it? Again, I've written main bar along longer span. You mention here crank 2 because this is second crank which you put. You're getting my point now. Explained everything I've explained you. Fine. Again, 1, 10, spacing you write 300. So here number of bar will be 17. Why? Because here I'll not do plus 1 because already plus 1 I've done it here. If you don't want to do plus 1 here, then you do plus 1 here. Anywhere you can do plus 1. But again, depends on site which they are putting first. See again, practically when you do on the site, it all depends, okay? Because if this is my slab panel, so the bar bender may put the first bar something like this. First bar if you put like this and give a crank here, then this number will increase. Otherwise, if the bar bender put like this, first bar in this way, crank here, then this number of bar will increase. So depends what is happening on the site. Okay, fine. But answer will be same, no problem. So 17 number, total cutting length, add everything, minus 2 into bend deduction, 2 into D, 2 into 10 you do. So total cutting length will be 7.427 into 17 into 1, which is 126.276. Since it's a 10 diameter bar, 126.27 multiply by 0.617, this will give you 77.9102 kg of a steel is required. So in this way, I've done the two-way slab, shorter span main bar, alternate crank, longer span main bar, alternate crank. After this, what is left out? Exactly, crank distributed in the shorter span, crank distributed in the longer span, and top extra bar is left out. Try to practice up to here. Rest all things is very simple. Whatever I taught you manually, whatever I taught you in the earlier, same thing I've done it here. Only the thing is values are changing. That's it. So in the next lecture, we'll do the remaining portion. So once that is done, after that, I'll teach you the other slab. This is one-way slab, and one-way slab. If you do, this entire slab BBS will be ready. Okay. So try to practice up to here. We'll see you back in the next lecture. Thank you.